Okay, let's write this in matrix form first. So my vector x is the vector. It doesn't matter if you use the square brackets or the round brackets. Like I kind of go back and forth with it. The Zill book always uses the round back brackets. I'm more used to writing square brackets for vectors, so I kind of go back and forth. It doesn't matter. So our variable matrix is xy. Then this equation is x prime, x vector prime is ax, where a is 2, 3, 2, 1. I want to solve the determinant of a minus lambda I equals 0. Lambda I, in this case, would be 1 minus lambda, 0, 0, 1 minus lambda. Or, I'm lying. Lambda I would be lambda, 0, 0, lambda. I want a minus that, so these guys here along the main diagonal get subtracted, or we subtract lambda from those. So this says 2 minus lambda, 3, 2, 1 minus lambda. That determinant equals 0. So this is our first step. We write our system in matrix form, find our matrix A, take the determinant of, and it's always the same thing, rewrite the matrix, but put minus lambda along the main diagonal. And then take this determinant. So remember, it's down minus down. So that's 2 minus lambda times 1 minus lambda minus 6 equals 0. Simplifying that, you could check these details on your own. That will become lambda squared minus 3 lambda plus 4 equals 0. Minus 4. It should be a minus 4. So that's lambda minus 4. Lambda plus 1 equals 0. By the way, this right here we call the characteristic, same thing there. That's our characteristic polynomial. Name that for the same reason it was back when we were one dimension. This is the higher dimension analog of what we were doing before. It's the same idea. That's our characteristic polynomial. We get two solutions. Lambda equals 4 and lambda equals -1. Let's number those. I'm going to call this guy number 1 and that one number 2. Those are our eigenvalues. Now, your calculator will do that for you. I could have just typed this matrix into my calculator and hit the eigenvalue button, and it would have spit out these numbers for me. So that you can always use that as a check. Now, let's find our, I need the space I have to erase. Let's find our eigenvectors. Now, there are two different ways to approach this. Remember, we had AK equals lambda K, or we had A minus lambda I times K equals 0. We could use either version, and I'll write it out both ways just for fun, to find our eigenvectors. Personally, I find this way much easier, using this version. They're mathematically equivalent, but you get to save a couple of algebra steps if you use this one. Okay, so our first, I'm going to do the second one first just because I get to write less negative numbers. Lambda 2 was 4. So I'm looking for the eigenvector that goes with that. So we're going to call it K1, K2. Plugging in here, I want 2, 3, 2, 1 times K1, K2 equals 4, K1, K2. So again, we can plug into this equation or this one. And let's actually write that out now. Let's do the multiplying. Multiplying through, I get 2k1 plus 3k2 equals 4k1. So doing the matrix multiplication. On the bottom, I get 2k1 plus 1k2 equals 4k2. I need to solve this system, but these lines here are not independent. They're redundant. This is actually the same equation twice. Whether you realize it or not, these are not independent. Because remember, any multiple of an eigenvector is another eigenvector. So there's not a unique solution here. So you can literally pick anything you want to be K1. I could call K1 anything besides 0. I could say it's 1, and then from that, solve K2. You can't solve the system. You'll get 0 equals 0. So if I pick K1 to be 1, so that would be 4 minus 2, I would get 3K2 would be 2. So K2 would be 2/3. So that would be a perfectly fine solution. I could say this solution that goes with lambda equals 4, so K for lambda equals 4 would be, what did I say, 1/2. What I find to be an easier way though, and we're going to get something that looks a little bit different, but it's still correct, is to use this version, a minus lambda I. So 2 minus 4, 3, 2, 1 minus 4 times K1, K2 equals 0. Then we get a 0 in there, and the things are a little bit easier to solve. So what's that? -2, 3, 2, -3. K1, K2 equals 0. And you can see clearly there that these two lines, if I multiply the first one by -1, I get the second one. These are not independent. So the two equations I write are really the same equation. So multiplying through, I'll get -2K1 plus 3K2 equals 0. And the second one gives me the same thing. It gives me 2K1 minus 3K2 equals 0. You can't solve that system uniquely. Okay, and then what I would do is move this guy over. So 3K2 equals 2K1. And then, so that I don't have to deal with fractions, just swap the coefficients. I need any solution here. There's not a unique solution. Any solution to this will work. So I'm going to make K1 equal to 3, that number there, K2 equal to 2. That way both sides multiply to 6. So my vector will be 3, 2. Just swap the coefficients.
Okay. Whatever
number is in front of the other guy, make the guy you have. And you can do that every single time. That's why this version is better, because you get down to this point here and you just say, okay, there's K2, there's K1. That's mathematically equivalent to the solution we just had. Okay, that was for lambda equals 4. Our other eigenvalue was lambda equals -1. So I could do 2 minus -1, 3, 2, 1 minus -1 times K1, K2. Don't worry about overusing subscripts. I already have my first eigenvector. I've already written it down. It exists somewhere. I know I've erased it now. But don't worry about, oh my God, can I use K1 and K2 again? Just don't confuse yourself. It's okay to reuse these. Okay, this will be what? 3, 3, 2, 2. K1, K2. So just multiply through, I'll get, this is supposed to equal 0, the 0 vector. So that's 0, 0. So 3K1 plus 3K2 equals 0. I only need the top one. So in other words, K1 equals negative K2. So I don't know, I'm going to go 1, negative 1. I could have just as easily said negative 1, 1.
Yeah.
I could have said 7, negative 7. I could have said negative E, E. Right, then my general solution will be x vector equals any multiple of that first eigenvector times e to the lambda t plus any multiple of that second vector e to the other lambda t. So that will be C1, 1, negative 1, e to the negative 1 t. That was my first eigenvalue. Plus C2, where we get 3, 2. E to the 4t was the other. That's what my general solution is going to look like. Some nasty looking thing like this.
Yeah.
We could, if we wanted to, squish this together and write this in a more standard form. I could say our variables were x and y. X is all the top stuff. C1, the top line, e to the negative t plus C2, 3. E to the 4t. And y is the bottom line. Negative C1 e to the negative t plus, I'm going to put my coefficients in front, 2 C2 e to the 4t. You might be tempted to go, oh, I can absorb those constants into my c's. No, you can't. This is now a system of equations. If we want to solve an initial value problem, I need to solve this with the 3 and the 2 and the 1 and the negative 1. I need to solve this for C1 and C2. Okay, that was doing a linear homogeneous DE with constant coefficients where we had distinct, unique eigenvalues. I'll make extra videos when we have repeated eigenvalues, something different happens, and when we have complex eigenvalues, something different happens.